On November 29th, 2024, a telescope orbiting 1 million miles from Earth pointed its infrared gaze at Saturn's north pole and found something that shattered 30 years of planetary science in a single observation. 10 hours. That's all it took. Not a month of patient data collection. Not a year of monitoring planetary behavior and atmospheric changes. 10 continuous hours of observation, and when the astronomers saw what Webb had captured in its sensitive infrared sensors, they realized they'd been missing an entire invisible category of phenomena on a planet we've studied continuously since before most of them were born. A planet visited and orbited by Cassini for 13 years of intensive study. A planet mapped by sophisticated instruments and simulated in supercomputers running millions of calculations. A planet we confidently thought we understood completely based on everything we'd learned. Suddenly, that certainty collapsed completely. The foundations shifted. What they thought they knew was wrong, or at least incomplete in fundamental ways. This isn't speculation or viral exaggeration designed to sell clicks. This is published research from 23 scientists across 3 countries, presented at international conferences, peer-reviewed and verified. And what they found shouldn't exist. Not according to the models, not according to the theories, not according to everything we thought we understood about how giant planets actually work in reality. These weren't minor adjustments to existing knowledge. These weren't subtle refinements requiring tweaks to equations. This was something fundamentally different. A phenomenon that the entire planetary science community had failed to predict, failed to observe, failed to even conceive of until a single infrared instrument revealed it hidden in plain sight. The James Webb Space Telescope was built with one extraordinary purpose: to see the oldest galaxies in the universe. Every single component, every optical surface, every infrared sensor was designed with cosmic history in mind. Its primary mission was to peer billions of light years into the cosmic past, to capture light from the earliest galaxies, to answer fundamental questions about the universe's origins. It cost tens of billions of dollars. It took decades to build. And as its schedule, its precious observing time, is fought over by thousands of astronomers from around the world. But sometimes, occasionally, when its schedule allows and its directors approve, astronomers redirect this most powerful infrared eye toward mysteries much closer to home, toward our own solar system, toward planets we think we already understand. On that November morning in 2024, with Saturn approaching its spring equinox, the moment when the planet's tilt relative to the Sun reaches a critical angle, a team of astronomers convinced Webb's schedulers to let them examine something that had puzzled planetary scientists for decades: the detailed structure of Saturn's upper atmosphere, particularly those enigmatic auroras that had never been fully explained despite being visible for centuries. What they expected to find was straightforward and predictable: a layered atmosphere organized by temperature and altitude, just as thermodynamics predicted. Methane clouds arranged in distinct bands. Ammonia hazes created by photochemical reactions. Auroras generated by solar wind particles crashing violently into atmospheric molecules, creating the characteristic glowing light show visible in Earth's upper atmosphere as northern and southern lights. The same fundamental process that creates our auroras, just scaled up to operate on a gas giant 100 times more massive than Earth. Nothing revolutionary. Nothing that would challenge the fundamental models built over decades of research by thousands of scientists. But the moment the data arrived and was processed by their analysis software, that expectation evaporated completely. Something was wrong, but not with the instrument, with their understanding of Saturn itself. Embedded in Saturn's brightest auroras, the most intense infrared emissions from its poles, there were dark structures. Not merely regions of reduced brightness that might represent instrumental artifacts. These were distinct, measurable deficits in infrared emission at specific wavelengths, where hydrogen ions should always radiate energy into space, always visible, always reliable. Imagine standing on a dark night and looking at Saturn's north pole through Webb's infrared sensors. Picture a brilliant, glowing halo of auroral light rotating steadily beneath the telescope's gaze, luminous and beautiful and following all known physical laws. And then imagine perfectly formed beads of darkness embedded within that brilliance, like pearls strung on an invisible wire running through the aurora. They stretched from 55 degrees north latitude all the way to 65 degrees north, precisely arranged in a geometric pattern, yet slowly shifting as Saturn rotated beneath the telescope's unwavering gaze. Some held their positions rigidly for hours, defying atmospheric winds. Others drifted across the planet's surface, moving with patterns scientists couldn't immediately explain. They were real. They were structured. They persisted. And they were absolutely impossible according to everything existing models predicted about planetary auroras. Cassini orbited Saturn for 13 long and remarkably productive years, from 2004 to 2017. It carried advanced infrared spectrographs and sensors specifically designed to study planetary atmospheres. It mapped Saturn's atmosphere in unprecedented detail, tracked massive storm systems, measured temperatures at different altitudes. The mission was extraordinarily successful and collected terabytes of data about every aspect of Saturn's behavior. Yet despite all this capability, despite all this accumulated knowledge, Cassini found nothing like the dark beads anywhere in its vast archive of measurements. Scientists weren't surprised at first. Cassini's instruments, while advanced for their era, simply lacked Webb's extraordinary sensitivity. These structures might be too subtle, too faint to detect with older technology. But when researchers went back to the archival Cassini data, armed with the specific knowledge of what to search for, something troubling became clear. The dark beads weren't hiding anywhere in the archive waiting to be discovered by a more careful search. They weren't there at all. This created a profound implication. Either these structures emerged in the 7 years since Cassini's mission ended in 2017, meaning they're brand new phenomena that only recently appeared on Saturn, or they are phenomena that only become visible when you observe with Webb's unprecedented infrared sensitivity and resolution instruments that simply didn't exist during the Cassini era. Webb showed us something Cassini couldn't see, something that should have been impossible to miss if it had been there, something that fundamentally shouldn't exist according to established models. The immediate question burned in every researcher's mind with almost painful intensity. What creates them? What mechanism could produce these structures? Planetary scientists had spent many decades understanding auroras in meticulous detail, building comprehensive models through direct observation and mathematical simulation. They understood precisely how solar wind particles interact with planetary magnetic fields, how the sun constantly ejects charged particles in a stream that flows throughout the solar system. They could model exactly how these particles get trapped by magnetic fields and spiral down into planetary atmospheres along magnetic field lines, cascading deeper and deeper until they collide violently with atmospheric molecules, exciting them and creating the visible light we observe as auroras. The theory was solid. It was built on fundamental physics that had been tested and verified repeatedly. It worked on Jupiter, where Cassini and other spacecraft had observed auroras for decades. It worked on Earth, where scientists had studied our own northern and southern lights since written history began. It had been tested and verified hundreds of times through observation and experiment. But nothing in that entire theoretical framework predicted dark beads. Nothing in the equations suggested such structures should exist. Nothing in the simulations showed these formations emerging from known atmospheric processes. The leading hypothesis centered on a phenomenon called Kelvin-Helmholtz instabilities. Here's how it works. When two distinct atmospheric layers move at different velocities, when the winds are moving at different speeds at different altitudes, when powerful winds shear intensely against each other at the boundary between them, waves form at that interface. Think of the exact moment, where two ocean currents collide head-on. The boundary becomes turbulent and unstable. Waves and eddies form as the water masses interact and fight against each other. Similar processes occur throughout planetary atmospheres. The physics is fundamental. These are well-understood phenomena, observed repeatedly in Earth's atmosphere during severe wind shear events, detected in Jupiter's colorful clouds through telescope observations, predicted with high confidence to occur on Saturn and every gas giant throughout the galaxy. They should exist on Saturn. They should create visible structures. They should be detectable. But Saturn's dark beads didn't follow the expected pattern at all. The geometry was distinctly wrong. The spacing wasn't what theory predicted. The distribution didn't match simulations run on the world's most powerful supercomputers. The darkness itself suggested specific chemical or physical conditions that remained frustratingly difficult to identify or explain. The hypothesis explained some features of the observations reasonably well. It explained none of the others. Some properties fit the theory. Other properties contradicted it directly. The beads remained partially mysterious, partially explained, fundamentally incomplete. Scientists were forced to confront an uncomfortable reality. They didn't understand what they were seeing. That's when scientists noticed something that complicated absolutely everything further and turned a puzzle into a genuine mystery. Lower in Saturn's atmosphere, approximately 500 kilometers below the ionosphere, a vertical distance equivalent to flying across an entire continent on Earth, in the stratosphere where different atmospheric physics govern the dynamics and behavior, Webb detected something extraordinary, an asymmetric star-shaped feature. Not a perfectly symmetrical asterisk like something drawn by a geometric computer, a four-armed structure emanating directly from Saturn's pole and extending outward toward the equator at distinctly uneven angles. The arms weren't evenly spaced around the pole. The brightness wasn't uniform across different arms. The entire structure appeared tilted and off-center, geometrically impossible according to the symmetric patterns that planetary models confidently predicted should dominate at polar regions. This star pattern rotated steadily with Saturn, locked to the planet's rotation. It maintained its orientation relative to the planet's powerful magnetic field with remarkable consistency. As Saturn rotated beneath Webb's continuous, unwavering gaze over hours and hours of observation, the arms appeared and disappeared in sequence, creating an animation of atmospheric motion, and a structure never recorded before in the entire history of planetary observation. Each rotation revealed the same pattern, modified slightly by atmospheric dynamics, but fundamentally persistent and real. Then researchers made a connection that sent shivers through the scientific community. The darkest regions of the ionospheric beads seemed to align precisely with the brightest arms of the star pattern 500 kilometers below. Not approximately, precisely. Two separate anomalies observed at two different altitudes, possibly connected through deep atmospheric processes we don't yet understand, or possibly coincidental overlap by pure chance. The scientists carefully distinguished between observation and interpretation, a critical distinction that separates science from speculation. One was proven fact, directly observed and verified. The other remained hypothesis, a plausible guess, but not yet confirmed by evidence. The star pattern appeared directly above Saturn's most famous and most mysterious feature, the hexagonal storm. This six-sided hurricane has persisted at Saturn's north pole for many decades, possibly for centuries. No one knows how long it has actually existed. It's one of the most geometrically distinctive phenomena anywhere in our entire solar system, visible in telescope observations and planetary probes. A perfect hexagon with walls of wind and a rotating center, defying simple explanation despite decades of study. Scientists still don't fully understand why or how a hexagon forms on a rotating planet when physics would predict a circular storm. Now Webb revealed an atmospheric structure hovering directly above this enigmatic hexagon like a phantom made of wind and energy. The connection was undeniable. Could the star pattern be waves propagating steadily upward from the hexagonal storm, carrying its influence higher into the atmosphere? Could deep oscillations and vibrations within that storm drive structure and organization into the stratosphere above, creating the star pattern through resonance and coupling? Could the hexagon's powerful rotation and internal circulation generate the star through some mechanism scientists hadn't yet conceived? Or was the proximity pure coincidence, two completely unrelated phenomena happening to overlap in the same location? These weren't rhetorical questions designed to inspire wonder. They were genuine scientific uncertainties, open questions without answers, puzzles requiring investigation and evidence. The researchers filed these questions away, documented them carefully, and prepared to present their findings to the international scientific community. When scientists from multiple countries gathered to discuss the Webb results, the conversation shifted immediately from wonder to concern. How many other phenomena were they missing? How many other invisible structures existed on other planets, waiting to be revealed by more sensitive instruments? The implications stretched far beyond Saturn's immediate mysteries. Every observation raised new questions. Every answer spawned new puzzles. The dark beads and the star pattern weren't isolated anomalies. They might be just the beginning of a much larger realization about the fundamental incompleteness of planetary science. Some researchers began examining their own models more critically. They ran simulations with deliberately incomplete information, wondering what would emerge if they removed certain assumptions. They discovered that many standard models relied on approximations that might not hold up under scrutiny. Simplifications made for mathematical convenience might be hiding real phenomena. The field suddenly seemed less settled than it had appeared just weeks earlier, before Webb's observations changed everything. But there was something even more intriguing and profound buried deep in the same dataset, something that had puzzled planetary scientists for decades and now took on new significance. For many years, careful measurements by multiple spacecraft and ground-based observatories had suggested something peculiar and troubling. Saturn's rotation rate seemed to be changing gradually over time in a way that shouldn't be possible. Not dramatically or suddenly in obvious ways, but measurably, detectably changing. Through accumulated observations, the planet appeared to be speeding up or slowing down by small but significant amounts over the decades, which shouldn't happen according to the fundamental laws of physics that have never been violated. A rotating body, in the absence of external torque or force, maintains constant angular momentum forever. It's one of the most basic principles in classical mechanics, the foundation of how we understand rotational motion. Saturn shouldn't be changing its spin rate at all according to this principle. And yet, the observations from multiple spacecraft missions and ground-based measurements from telescopes on Earth clearly and consistently showed it was slowly and persistently changing over the decades in measurable ways that challenged existing understanding. Webb's high-resolution measurements of Saturn's auroras revealed a possible answer to this long-standing mystery. The auroras were far more complex and intricate than previously understood or modeled. They interacted with the upper atmosphere in ways that created subtle forces, small but measurable and real forces that could translate into torques affecting the planet's overall rotation rate. The energy from the solar wind, flowing constantly from the sun and channeled through the magnetosphere's magnetic field structure, delivered forces to the upper atmosphere that eventually propagated downward through the layers and into the rotating body beneath. Tiny forces, barely measurable in isolation, each one insignificant, but cumulative, ongoing, persistent. Year after year, they add up and accumulate into real effects. Webb didn't solve the rotation mystery entirely or definitively, but it pointed toward an explanation that unified multiple previously disconnected observations into something coherent and sensible for the first time in decades of research. These discoveries reverberated powerfully through the entire planetary science community because they implied something profound and deeply troubling. Fundamental gaps existed in humanity's understanding of planetary atmospheres. If Saturn's upper atmosphere contained structures and complex processes that current models didn't predict, that existing theory didn't anticipate, what did that mean for Jupiter? Jupiter is the largest planet in our solar system, surely experiencing similar processes: magnetospheric interactions with the solar wind, auroral precipitation, atmospheric circulation patterns. Yet no astronomer had looked at Jupiter with Webb's extraordinary infrared sensitivity and comparable detail. No one had pointed Webb's instruments at Jupiter for similar extended observations. If Jupiter harbored its own collection of unexpected structures, its own hidden phenomena, the implications multiplied exponentially for the entire field. What about Uranus and Neptune? The ice giants have been studied far less intimately and thoroughly than Jupiter and Saturn throughout human history. Uranus was only discovered in 1781. Neptune was discovered in 1846. We've barely glimpsed these worlds through telescopes. If our understanding of Saturn's atmosphere remained incomplete and flawed despite decades of intensive research and multiple spacecraft missions, how many surprises waited waiting in the stratospheres and ionospheres of those distant worlds? These planets orbit at the very edge of our solar system, receiving minimal attention from the general public, often omitted from documentaries and popular discussions of the planets. Yet they are worlds too, complete worlds with their own atmospheres and dynamics, and we understand them poorly. The implications extended far beyond our solar system, to exoplanets orbiting distant stars. Astronomers have discovered thousands of giant planets orbiting distant stars throughout the galaxy, many of them similar in size and composition to Jupiter and Saturn. Our entire understanding of these alien worlds has relied entirely on models and theories built from observations of our own giant planets within our solar system. If those models underestimate the complexity and behavior of Saturn's or Jupiter's atmospheres, how reliable are our interpretations and conclusions about distant worlds? Could scientists be fundamentally misinterpreting data from exoplanets because the theoretical framework was incomplete? Are we seeing all the features of distant giant planets, or are we missing entire invisible categories of phenomena, just as we were with Saturn before Webb? This is the terrifying part, though not terrifying in the conventional sense of fear or panic. It's intellectual vertigo. It's the dizzying realization that a well-established discipline, a field of study with decades of accumulated knowledge, rests on incomplete foundations. Planetary scientists aren't wrong about the basic physics governing giant planet atmospheres. The fundamental equations of thermodynamics and fluid dynamics remain absolutely valid and always will be. But their application to real planetary systems, to actual planets like Saturn existing in reality, might be oversimplified or incomplete. The models might be missing crucial feedback mechanisms, unexpected interactions between different atmospheric layers, phenomena that only become apparent when you observe with sufficient resolution and sensitivity. Scientists collectively thought they understood Saturn. They were overconfident in that understanding. They were humbled by evidence. But this is how science actually progresses and advances in the real world. A theory is carefully developed over years and decades. Observations are made systematically through experiments and telescopes. When observations don't match predictions made by the theory, scientists don't immediately declare the theory failed completely. They ask harder questions, better questions. What aspect of the theory is incomplete or oversimplified? What phenomenon did the model fail to account for adequately? What process is more complex and subtle than previously assumed? The dark beads on Saturn represent this exact pivotal moment in the scientific process, not a crisis of confidence, but an opportunity for advancement. This is how understanding deepens. This is how science becomes better. Future observations will be absolutely essential if humanity wants to understand what's happening on Saturn. Webb will continue monitoring Saturn intensively as the planet progresses through its seasonal cycle over the coming years, accumulating more data points and more evidence. Additional observations accumulated over months and years will reveal whether the dark beads are permanent, persistent features of Saturn's atmosphere, stable structures that endure across seasons, or transient, temporary structures that vary and change with seasonal shifts in atmospheric circulation patterns, driven by changing sunlight angle. The star pattern will be monitored carefully for any changes in geometry and shape, brightness and intensity, position and drift across the planet's surface. Every variation, every change, every subtle shift could constrain and narrow down the competing hypotheses about their actual origins and what mechanisms drive their formation and persistence. The Hubble Space Telescope will contribute complementary visible light observations from its unique orbital perspective, providing data in a completely different wavelength regime that Webb cannot access due to its design. Ground-based infrared observatories scattered across Earth and positioned at high-altitude locations will conduct supplementary observations to provide additional confirmation and independent verification of Webb's data. These ground-based observations help rule out instrumental effects specific to any single telescope. Researchers will revisit massive archival databases containing years of data from Cassini and other Saturn missions, searching meticulously for any precursors or earlier manifestations of these structures, any subtle hints that they might have existed previously but simply been overlooked by less sensitive instruments that lacked Webb's extraordinary capability to detect faint infrared emission. Such archival searches sometimes reveal that phenomena were present all along, simply invisible to earlier technology. Theoretical models will be revised and updated systematically based on new observations and accumulated data. Computer simulations running on the world's most powerful supercomputers will be executed with new parameters, new assumptions, new coupling mechanisms between atmospheric and magnetospheric processes that may have been neglected or oversimplified in earlier models. Scientists will try different hypotheses, different explanations, different physical mechanisms operating in simulation to see which ones produce structures similar to what Webb observed. They'll test whether Kelvin-Helmholtz instabilities could work under different parameter regimes. They'll examine whether coupling between the magnetosphere and upper atmosphere creates unexpected resonances. They'll investigate whether deep convection in lower atmospheric layers could drive structures visible at higher altitudes. The goal isn't to replace the existing atmospheric model entirely with something completely new or revolutionary. Rather, it's to refine and improve understanding incrementally, to add layers of complexity where necessary and justified by evidence, to create a more complete and accurate representation of how giant planet atmospheres actually behave in reality, rather than in simplified mathematical models that ignore important processes. The dark beads represent neither catastrophe to scientific knowledge, nor trivial puzzle requiring quick solution and closure. They occupy the precise space where science advances most meaningfully and productively, at the intersection of observation and theory, where surprising unexpected data forces reassessment of fundamental assumptions held by the scientific community for decades. Scientists aren't terrified in the conventional sense of running from the problem or denying its significance and implications. They're energized by it, fundamentally, motivated by the mystery and the unknown territories ahead, driven by the deep certainty that something important and fundamental remains to be understood about planetary dynamics, magnetospheric interactions, and energy transfer in giant planet atmospheres. This is the moment that makes science exciting and worth dedicating a career to. This is the moment that drives researchers forward, that motivates them to pursue knowledge despite uncertainty and significant challenges. This is why they became scientists in the first place, to solve mysteries and advance human understanding of the cosmos. And that is the real discovery here, the most important revelation. Not simply that Webb found strange structures on Saturn floating in its atmosphere. It's that a planet we've observed continuously for centuries with telescopes, visited with multiple spacecraft, studied with sophisticated instruments across decades of missions, can still surprise us completely and unexpectedly, can still reveal hidden aspects of itself that contradict our expectations and assumptions, can still demonstrate that despite all our technological advancement and innovation, despite all our theoretical knowledge, accumulated carefully over generations of research, the universe retains profound mysteries in our own cosmic backyard, in our own solar system. The story of Saturn's dark beads is far from finished. The observations have been made by Webb and recorded precisely. The data has been compiled and verified thoroughly. The research teams across multiple nations are analyzing the data carefully, debating different explanations, proposing new hypotheses, but fundamental questions remain unanswered. What creates these structures physically? How do they relate to the star pattern observed far below? Why didn't earlier instruments detect them before Webb? What do they reveal about energy transfer and dynamics in giant planet atmospheres? What other hidden phenomena might Webb discover when it looks even more carefully and systematically at other worlds orbiting our sun? The answers will emerge through continued careful observation of Saturn across many years, continued rigorous analysis of the data collected, continued collaboration and cooperation between scientists across different institutions and nations worldwide, freely sharing data and ideas and insights about what they discover. In the meantime, we exist in a state of productive uncertainty and genuine anticipation about what the future will reveal. We know something important is happening on Saturn. We know it challenges existing models significantly and fundamentally. We know it points toward more complete and accurate understanding of planetary science. And we know that the universe is far more complex and interesting than we typically assume in our everyday lives and casual thinking, even in planets orbiting our own sun, even after centuries of dedicated study and observation, even with the most powerful instruments humanity has ever built and deployed into space. That's the real wonder of true discovery and scientific inquiry. Not fear of unknown dangers, but genuine intellectual humility before a universe that continues to surprise us constantly, that refuses to be fully understood or completely mapped, that demonstrates with every new discovery made how much remains to be learned and explored. It's what drives scientists forward relentlessly despite challenges and uncertainties. It's what makes science meaningful and genuinely worth pursuing with dedication, passion, and commitment to truth. We thought we knew Saturn completely. We thought we understood how planets actually work at their fundamental core. We thought centuries of telescopic study and decades of spacecraft missions had revealed everything there was to reveal about the gas giant in our cosmic neighborhood. We were confidently, thoroughly wrong. And that wrongness, that humbling realization that we've been missing an entire invisible category of atmospheric phenomena on a planet we've studied since before telescopes were invented, that might be the most important discovery of all. Because it means we're still asking the right questions about the universe and our place in it. It means the universe still has secrets waiting to be revealed to us through careful observation and rigorous analysis. It means that even with all our technology and knowledge, all our confidence in our models and theories developed over generations, there's still mystery waiting patiently at the edge of discovery. Saturn's dark beads aren't just strange atmospheric formations or curiosities to catalog and forget. They're proof that wonder isn't something we outgrow as science advances and becomes more sophisticated over time. It's something that deepens and multiplies the more we learn, the more we understand, the more we explore with better instruments. Every discovery opens new questions inevitably. Every answer spawns new mysteries. This is the beautiful, endless, and rewarding cycle of scientific inquiry and discovery. The real significance of Webb's observation isn't that we found something unexpected on Saturn. It's that we proved we still have fundamental gaps in understanding places we thought we knew well. This should humble us. It should inspire us profoundly. It should motivate the next generation of astronomers and planetary scientists to look even more carefully, to ask better questions, to build even more advanced instruments that can reveal phenomena we haven't yet imagined.